In the last lecture, we started talking about this interesting topic of peer-to-peer networks, and we said that it started out with Napster, which was a little bit of a centralized system where different peers essentially contacted the server and told the server what files they had, and anybody who wanted a particular file would search in this server and they would find out which peer had those files and then they would download it from there. So this was the first generation, and the central point was not just a technical point of failure but also a legal point of failure, because the government of the US, or the courts at least, they asked Napster to shut down because they were violating copyright rules and so on. Then we said in the next generation there was something more decentralized than Napster, which was Nutella. And in Nutella, essentially you could think of this peer-to-peer network as a graph. So initially nodes contacted some set of peers and connected to them, and effectively there was a graph of these peers. So if somebody wanted to search for a file, essentially the way to do it was to do a broadcast. So you would broadcast the query only to a certain depth in the graph, and you would get replies about who had what information, maybe matching with the search, and then you could download it from there. Right, so this was, but of course the problem here was that you had to do this brute force search, which could potentially flood a large part of the network. So what we wanted to come up with is to have a system like this where each peer is only connected to a few other peers, so that they form a graph, but we wanted the search to be much faster. So how can I quickly find out where the information is which I want to find? And we started discussing the third generation of peer-to-peer networks. So we said essentially what we want to do is we want to store information cleverly. So maybe there is a file at a particular node, right? Maybe we said this node Q has the file F1, and of course there is no way for anybody to know that Q has F1. Q would have to tell that information, but we want Q to store that information somewhere in the network where it says that I have F1. Okay, it doesn't actually necessarily have to store F1 somewhere else, but it stores the information that it has F1, and it stores it in some place which is sort of a place that other people can find easily. So what we said is we are going to map these file names, or you can think of these as some keywords even. We want to store this information in some way. We want to map it to the IP addresses in such a way so that everybody knows this mapping. So we said we want to do the mapping such, let's say that the mapping maps F1 to this IP address of E, and anybody who wants to search for F1 can do this mapping and they can find this node E, and E is going to tell them where this file is stored. Right, so if A is searching for that file, it should be able to get to E, and of course if Q wants to tell anybody else that it has this file, it will record that information in E. Okay. And what we said is we want to have this mapping, and we want it to be some sort of a it shouldn't map all these files to the same IP address, because that would give too much of work to that particular node. Everybody would be querying it. So what we said, we want to sort of randomly map these files to these IP addresses. And we began saying that let's use a hash function. So, and of course we won't go into details of what exactly a hash function is, but effectively what it does is that it can take any bit string of any length and it's going to spit out a number of fixed length. So let's say m bits. Right. So what we do is we take this F1 or F2 or whatever it can be of any length of bits, and we are going to get the hash of that function, which is some map in a particular space. Right. So we said, of course, if we take one example is you can take 32 bits and then you can say what I'm going to do is I'm going to store information about a particular file in the IP address closest to that. Okay, so this of course had its own issues, that because IP addresses may not be uniformly mapped here, and certain IP addresses may again get too much of the work, right? So what we said is that let's map both IP addresses and file names to the same space. Okay, the output, let's say the space of 2 to the power of m, or m bit space. So there are 2 to the power of m different numbers over here. Okay, so we take the hash of the file. So let's say f1 gets mapped here, f2 gets mapped here, f3 gets mapped here, and this is essentially the mapping of the IP addresses. So let's call the files, let's just call them objects, and so this, if you look up any paper or a textbook, they may use terms like this. And let's say the nodes are let's say all the peers. We're just going to call them nodes. So this is going to be a node ID, and this is an object ID. So what we're going to do is we are going to store an object in the node whose node ID is the closest to its object ID. So F3, in this particular example, F3 should be, information about F3 should be stored in node C, right? Not necessarily F3 itself, but information about where F3 may be found should be stored there. And similarly, F1 information should be stored at E, and F2's information should be stored at B. Okay, so this is a clever idea. So you would expect that these node IDs and object IDs to be uniformly distributed, I mean randomly distributed over here on this circle. So effectively each node would sort of get roughly equal amount of work to do, okay, because people would query it. If people want F3, they are going to query node C to find out where it is. So how do we do this? I mean, of course the mapping can be done, but suppose a particular node, we said node Q has F1, it can find the object ID of F1, obviously it just has to take the hash. Hash is a well-known function, and of course E can of course find its own node ID, that's fine, but how does node Q, who has F1, find out that this is the closest node ID to this object ID? Because after all, it's not a clique or anything like that. It's not that every node is connected to every other node, because that is simply impractical to do. There could be millions of nodes in the peer-to-peer network. So you might be connected to 3-4 other peers, and how are you going to find out who is closest? That was one problem. And secondly, we said that nodes might actually leave the network, right? So what if node E, you suppose Q does the hard work of storing that information about F1 at E, but then E just closes his peer-to-peer application, or he switches off his machine or something like that, and then he's gone. So even though Q is connected to the network and has file F1, then people will not be able to find where it is, because the next closest node ID to this particular object ID may not have that information. So these are some questions we have to look at now, and of course many solutions were proposed, and they are sort of the basis of a lot of peer-to-peer networks which are out there. So let's see. So let's just write down some of the rules. Okay, so we want to store information about where an object is stored at a node whose node ID is closest to the object ID of the object. So let's look at this space and think how we might want to do it. So this is the space. We start out with 0 here. And we go to 2 to the power of m minus 1 over here. Right? We go around this circle. So there are going to be certain number of nodes and objects mapped over here. So let's say that there are objects mapped over here. And at the same time there are also nodes. These are the node IDs. Now let's say this corresponds to A. Right, and it may have some particular number which is mapped over here. This is the node ID of A. And let's say that this corresponds to B, and this corresponds to, let's say, C. And let's say we have a peer-to-peer network where A is connected to B and C, and B is connected to D and so on, right? Or C is connected to E and so on. So let me draw that. So that means, so these are the actual TCP connections which are set up between these peers. So A has live TCP sessions with these two, so it can send messages to B and C, and similarly B and C can contact A. Right? So this is the actual TCP connections and this is essentially the peer-to-peer network. So let's say that even C is connected to D. Okay? So what would it look like? So A is connected to B and A is connected to C, and let's say that this is D and this is E. So B is connected to D, and we said that C is connected to D, and C is also connected to E, we said. Okay. Let's just say that D is connected to F. And let's say that this is F. Let's say maybe this corresponds to G. Right, so E is connected to G and D is connected to F. So this is the actual peer-to-peer network. At the transport layer I'm showing the network, what it looks like. These are the TCP connections, and if I plot that same graph over here in this space, it would look like this. So suppose this is where the hash of, let's say, hash of f1 ends up. So this is the node ID of E, which is closest here. So how is, let's say, how is A going to find out? So suppose A wants to find out about F1, and A of course is connected to B and C, right? So how are we going to find out where F1 is stored? Because we said that information about F1 is stored in E. So some Q we said has F1, right? And so suppose suppose A wants to find out which node is closest to this particular point in the space. Okay? Because he's interested in F1, how is he going to do? So definitely he has to query his peers whom he's connected to. He could ask B and C, right? And let's see, in this particular case, let's say C happens to be closest to this point, yeah, among these two. It could be that there are peers of A whom A is connected to, who might be even further away from this point. Okay. So what we are going to do here is something intuitive that you might guess yourself. Why don't we try to actually send messages to people whom we know who are closest to this point in this space? Okay, so I'm abstracting it out. I want you to think in this space of 0 to 2 to the power of m minus 1. In this particular space, I want to route a message, and I want to send it to nodes who are closer and closer to this point where I've shown over here h of f1. I want to route the message there, and hopefully I will be able to finally send the message to whichever node is closest here. So that's the idea. So the idea is route messages. Essentially this is a query message closer to this point h of f1. Okay, in this virtual space, till we reach the node E. So how is A? So suppose A wants to find out where F1 is stored. Okay, so what is he going to do? A finds its connected peers. Let's say A finds which of its connected peers is closest to E. So if A wants to find out where F1 is stored, it essentially wants to route a message closer to this point in the space. So it finds which of its connected peers is closest to E. And the term for these connected pairs of A is called the leaf set of A. Okay. So A is connected to B and C, and so clearly C is closest to this point. So it knows the node ID of C, right? Because it knows the IP address of C, so it knows which one is closest. and so it's going to send a message to C. So let's say the query goes this way, and now C is going to do the same. So this repeats till the query reaches a node who has no connected peer who's even closer to h of f1. Right? So obviously in this particular case we reach E, and E is connected to G. I mean, the E is connected to G and C, and neither of these two peers is closer to this point. Right? So we continue this procedure until we reach some node like E, which is closest. Okay? So now, of course, you might say, what if there is another node here? Maybe there is another node which is closest to this point, but E is not. Maybe E is only connected to C and G, and it doesn't have a way of getting to that node. Right? So we have to ensure that something like that doesn't happen. Okay? And what we want is that this node where we stop, we want this node to actually be the node which is genuinely closest to h of f1. Okay. So how are we going to ensure that? Okay, and also we want this search to be quite fast, and so we said we want the number of times this query is forwarded to be something like order of log n. So a number of peer-to-peer protocols were proposed, which had a lot of these properties which I am saying that we should have, and also they were robust to node failure and so on. So we look at one of them, and one of them it's called Pastry. So Pastry said, first of all, one of the rules, it says that in a leaf node of let's say for node X, include the nodes immediately to the right and left of that node in the space. So include certain number of nodes L over 2 closest nodes on either side, let's say, in the virtual space. So how is this going to help? So if you have, let's say this is where I've used a different color, let me just reuse the same one. So let's say that this is where X is, and let's say that you have some nodes like this. So if L is equal to 2 as an example, then X should have these two nodes in the leaf set, in its own leaf set. So how are we going to ensure that? Okay, but suppose we are able to do this somehow, then are we guaranteed that this algorithm is actually going to find the closest node to h of f1? So indeed you can show it's kind of obvious that that would be satisfied, because we said that E should have the closest node on its left and right on this circle, right? And so if at all one of its peers was closer, okay, it would forward it to that one, okay. But if indeed suppose there was an, let's say, some node K over here which was even closer, then this would be a neighbor of E, right? It would be in the leaf set of E, and E would be able to send it over here, okay, because the node on the immediate left and the immediate right, we said, has to be in the leaf set of E, okay. So this is going to guarantee that we will be able to find whichever node is closest to h of f, okay. Okay, so you can never, it's never going to happen that we end up, this particular algorithm is going to get stuck at a particular node which is not the closest, and it doesn't know any other node which is even closer, right? That's never going to happen. Okay, so this solves the problem. So this ensures that the routing protocol which we used gets to the node closest to h of f1. Okay. So this is good if we can achieve it somehow. Okay, so how are we going to find out who's on your immediate right and left? That seems a little bit tricky, right? Of course, to be a little bit on the safe side, you would normally want to have L larger than 2, because and we'll see that certain nodes might drop out from the network, and if L is actually equal to 2, then that might create problems. Yeah. Anyway, so what we are going to do is that, so what Pastry ensures that leaf set of any node is of size L. Of course it has to be L because you have L by 2 on your right and L by 2 on your left as part of your leaf set, but you also have a few others, and you ensure that you have at least something of the order of log and other peers. Let's say that n is the number of nodes, number of peers in the network. And right, so this is taken care of, and as they prove in their paper that these nodes will be fairly well distributed around this circle, right? So you will have few people on your left and on your right, but you will also have a few others distributed around this circle, and that will help you zoom in very quickly to the location where you're trying to search, right? So you want to find the node closest to some point in this space, and because these peers are very well distributed around the circle, you can very quickly do that. Okay, the routing algorithm ensures that you can actually find the node closest in roughly order of log n forwards, okay, of the message. So just to clarify, that by this routing over here, I don't mean layer 3. Here we are routing among the peers, Okay, it's in the peer-to-peer network we are routing. So this is not happening at the layer 3. This is a sort of routing happening at the application layer. You can think of it over this peer-to-peer network. Right? So suppose we didn't have these peers. So maybe just as an exercise we will see. So suppose we just had nodes on the right and on the left. So we had this large circle and these were all the peers. And each of them was only connected to the person on the right and on the left. Right, there were these, what I'm showing over here are the only connections that are there in the network. Now suppose, let's say that this corresponds to A, and let's say that h of f1 is somewhere here. So the question that I want to ask is, first of all, the routing algorithm that we discussed earlier, is it going to end up at E or not, right? And also the question is, how long does it take to reach here? Okay, so we said that E is closest to this point, let's say. So what are we going to do? So maybe let's say that this particular peer is closer to E than this one. So what's going to happen is that the message is going to go this way, right? And they're going to keep forwarding to somebody who's closer and closer in their leaf set. And finally it reaches E, and E sees that this neighbor is further away from X, right? And of course this one is also further away. So E identifies itself as being the closest node, right? So this particular connectivity is going to guarantee that we are going to find the closest node to F. We are never going to miss it anyhow, okay? Because everybody is connected to the node, the immediate right hand. So how many message forwards do we need, and how many messages are sent to finally discover E? Well, so it's going to be something like order of n, right? So you can clearly see that it's going to take that many number of messages. So if you want to speed it up, it's better that A is connected to people, let's say, who are well distributed over this space, so that instead of going this way, he could directly send the query to, let's say, or in fact it's going to be this one over here, because this is the peer who is closest to F1, and this particular peer is himself going to send it, let's say maybe this one is directly connected to E. So very quickly you would be able to find the node which is closest to this one. Right, so somehow we have to ensure that this leaf set is well distributed around this circle, and different protocols like Pastry and others ensure that. Okay, so the question is how we've sort of reduced the problem a little bit. So we are saying that everybody has to know the person who's immediately left and right of it, right? And in fact, of course, there is this factor of L, so you need to know L over 2 on your right, L over 2 on your left. So how are you going to do that? Okay. So this is a tricky question, because you sort of know what we want to do, but how do we get there? So let's think how we would start up. So suppose we have a network where this is true. Suppose the peer-to-peer network already has the property that leaf set of all nodes contains L over 2 on either side of the node. L over 2 closest nodes on either side of the node. So suppose this is already true. Okay, and of course when you have one node in the network, that is true. So it's sort of, we're going to use some sort of an induction idea here. Given this is true, can we ensure that if new nodes join the network, that this particular condition will still hold true? Okay, so we are saying that there are all these nodes and so let's say this node knows L over 2 on this side and it knows about L over 2 on this side. Suppose L is equal to 4. Now a new node joins and let's say that node is going to be here. This is node X. Now we want this new node to also have a certain number of nodes on the left and on the right. So how is it going to do that? So this node comes into the network initially. Let's say that it's only connected to this peer. Okay, so for bootstrapping it has to know some set of peers. So what we do is we route and we find out, using the same routing protocol we had earlier, we find out which node is closest to this. So let's say that this is node Y. So new node X routes a message to find node whose node ID is closest to its own ID. Right, and so it's going to do some sort of a routing and maybe the route is going to go this way and finally it ends up at Y. Okay, so it reaches Y this way. Okay, so now we said that X needs to know two people, at least two people on the right, two people on the left, and who has that information? Well, we said Y has that information. Y knows these two nodes and it also knows these two nodes. So it finds out from Y, it finds out Y is to the left of it. So it says, okay, you tell me one of your neighbors to your left, the immediate one, and you tell me both your neighbors to the right. Okay, so from Y, X determines L by 2 nodes who are closest to it on the left and right. Okay, so straightforward enough. You find out who is closest to you and that person already has the information from our assumption that already before the node joining we have this property. Right, and of course if you think of it, initially you start with one node in the network and the property is true. So you keep adding more and more networks and the property is still going to be satisfied. Okay, so this is one way to think of why you would have this property to be true. Okay? And once we have this property, it's good because you can always you're guaranteed to be able to find a node which is closest to any particular point in the space. So if we said if Q wants to store its information in the node closest to the file that it has, right? Let's just try to be explicit. So this is, let's say, Q, and Q has F1, and let's say that the object ID of F1 is here. So it finds out which node is closest, let's say E over here, and it would have to route the message. It might go through various other nodes, and it reaches E. Okay, so the query has Q's information. So E finally realizes that it must be closest to this point because there is no other neighbor of it, no other node in its leaf set closer. So it will directly reply to Q. You set up a TCP connection, and you will actually store information. Q will send information to E, and right, so Q tells E that it has F1. And somebody else who's wanting to search for F1 will do the same thing. He will determine whichever node is closest here, and he will ask that node where is F1 stored, and that node will reply with the appropriate information. Okay, so I'll just write that down. Similar procedure to find where F1 is stored. So this method of storing information and looking it up is called a distributed hash table. So if you're familiar with hash tables, you'll see the analogy. So with the hash table, when you're searching for something, you would find the hash, and you would look up in an appropriate location, and you would find the information you're searching for. Here the hash table is not local, it's sort of distributed around this network. The hash, you're going to use these hashes to find an appropriate node which has the information, and that's why it is called a distributed hash table. Okay. So most of these methods, Pastry, and there's another method, Tapestry, and there are lots of other methods which were proposed, Chord and so on. So I think the other names, if you're interested, you can look it up. Chord, Tapestry, Pastry, and so on. Okay, and one of the authors of the textbook, Peterson, I believe, was an author of one of these methods. I forget which one. And there is another person, Peter Druschel, who was on my PhD thesis committee. He too was one of the inventors of one of these, right? So anyway, so this was really hot at that time, late 1990s, early 2000s, and so on. And these papers are probably cited thousands of times. Okay, very popular papers. So this is good enough, and so we have to deal with the issues. I mean, how do you speed up this search? So we said that when we want a particular node to have not just a leaf set of people on the right and left, but you want to have nodes fairly distributed. So let's think about X. So X sends it to, let's say, node A over here. X is connected to A in the network, right? And let's say that this is B and this is C and so on. So A is connected to many people, but let's say it is also connected to B, and B is connected to C, who is connected to Y, right? So when this message is propagating over here, right, so X is joining the network, so it could get some information from these nodes as this is propagating. This is the join message, right? And it could get information from these other nodes about who are their leaf sets. Okay, so one way for X to populate its leaf set is that it can add A, B and C and Y to its leaf set. Sorry, this is X. And the authors of Pastry showed that this is going to essentially ensure, because we said the search takes log n sort of messages, right? So it takes you roughly log n hops to reach Y, and if you add all these nodes to your leaf set, then that's how you get your log n other nodes, right? Besides the ones on your right and on your left. So you add these to the leaf set when you join itself, and what they showed is that these will be fairly well distributed also. Typically, once the network gets large, these will be fairly well distributed over this circle, and that will ensure that you can do a fast search, okay, when you're searching for any particular location in this space. Okay. So what to do if a node fails? Okay, I'll just say this ensures that the leaf set is of size order of log n plus n. Now let's think what might go wrong if a node fails. So this is a particular node, let's say X, and it has information, let's say, about where file F1 is stored. And that's because the hash of F1 is close to it, and there's no other node which is closer. Let's say this is some node Y, and let's say that node Q is the one which has F1. So Q has routed a message through this network, and it has found X, which is closest to this point in the space, and so it told X that it has F1. Now if X fails, then we have a problem, right? Somebody might just switch off the machine of X. So then what happens? Well, then somebody else who's searching for F1 might route a message, and let's say that the next closest one is Y. Let's say there is another node here which is Z, which is further away. So if somebody routes a message, they will end up at Y if X fails. And Y has absolutely no idea about where this file is, because Q had only stored the information in X. So this is a problem, and so what we need to do is we have to have some redundancy, because of course if X was gracefully going to leave the network, then it could inform the next nearest neighbor, let's say Y, and it could send whatever information it had to Y. But the exit of X may not be so graceful, it might just suddenly leave the network. So we need some redundancy. So what we do here, what Pastry suggests is that Y stores information of 2 nodes to the right and 2 nodes to the left. Okay, so closest to Y. So this means that whatever would normally be stored at X, for example, where F1 is stored, that information would be stored at Y, and also Y would store information at Z. Right? So let's say that there were 2 other nodes here. So this is what they recommend is done. So Y has a little bit of extra information than what it would normally have. Okay. So of course Z would store about whatever information would normally be there at X and Y and at, let's say, some other nodes, right, C and D. Okay. So it's not that all the information at X is stored at Y. We have to be careful, because otherwise with this rule everybody would have the same information. Because suppose I say that, suppose the rule was that Y has to store everything at Z, then whatever was there at C and D would also be at Z, which would be stored at Y. Right? So that's not what we do. What would normally be stored at Z, based on what we discussed earlier, only that information would be also stored at Y. Right? And similarly for A, B and so on. So every node does this. So now if X fails, it's not a problem, because somebody would route to Y and he would be able to recover the information about where F1 is stored. Right? So this has to be done quite carefully, and so nodes have to know who are their neighbors. Right? So we said in the leaf set they have some neighbors on the right and on the left. But what is recommended is that every node actually sends keep alive messages to its to the others it is connected to, just to know that they are alive. Right, and so this is important, because suppose X fails, we are robust to the fact that X fails because Y has that information, and in fact A also has that information and so on, right? Z and D would also have that information. But Y needs to now also store information which is there at D according to this rule. Because if X goes, then it has to get information from the 2 nodes to its right. Okay, so in case X goes down, what it does is it asks Z who is the next person to your right, and D also becomes part of the leaf set. Of course, if it may have already been part of the leaf set of Y, but if it is not, it becomes part of the leaf set, and Y would ask D for whatever information it has and stores it at Y. Okay, so all peers keep alive messages to the peers they are connected to. If any node, let's say, uh, two nodes to right or left fails, then it finds out about nodes further away, and ensures that this is true. Okay, so what I mean is that if X fails, then Y will find out about D and it will get information from D. Right, so this is the basic mechanism of how these peer-to-peer systems work using distributed hash tables. It's a very clever idea where we create this virtual space where we embed the files and the IP addresses of various nodes, and we have a quick way of looking up where information is stored. Right, and of course we have to make it robust to certain number of nodes failing and so on. Okay, so this is sort of the nuts and bolts of it, and of course if you are more interested you can study how BitTorrent works, the more advanced schemes, and I'm sure most of us have already used some of these peer-to-peer systems for downloading files and so on. Right, so this is an important topic in the application layer which I wanted to cover, and we look at other issues in the next class, at the other issues at the application layer.